Solutions of gases in water. How soda pop gets its fizz. Personally, I really like that fizzy taste. A can of soda is an example of a solution in which a gas is dissolved in a liquid. So the liquid is the solvent is water, and the solute is carbon dioxide. Most liquids that are exposed to air do contain some dissolved gases. You can see this if you take a clear glass measuring cup of water and put it in the microwave. Long before it boils, you see these little teeny tiny bubbles coming out as it's heating up. That's not boiling, that's the dissolved gases coming out. Most faucets at home have what's called an aerator on them, and it makes sure that the water is getting mixed with air as it comes out, because water that's aerated tastes better than water that doesn't have any air dissolved in it. We know that lake water and seawater have oxygen dissolved in them, or the fish would be dead. When we first moved to the Central Valley, we got some goldfish, and they seemed to be having trouble breathing because they were at the top of the little bowl gasping. You know, I'm like, what on earth? So I go online and look stuff up. Well, goldfish are cold water fish. But, you know, it was summer and it was hot, right? You know, it's like 80 degrees in the house, so the water in the aquarium was 80 degrees. But they wanted to be more like 72 degrees. I'm not running my air conditioner to keep the goldfish cool, right? So fortunately, I did find out that they adapt after a while. But the solubility of oxygen in the water also depends on temperature. And so at a higher temperature, there's less oxygen. And those poor goldfish were having trouble breathing. They got over it after a while. They got used to it. And they didn't die. So no goldfish were harmed. But that's why you can have thermal pollution. You have a big factory that's dumping hot wastewater into a stream, and that can have a huge impact on the fish and other wildlife in the stream because it raises the temperature and it affects the amount of dissolved oxygen. Your blood has dissolved gases: nitrogen, oxygen, carbon dioxide. And, you know, if you're in the hospital, they're really concerned about how oxygenated is your blood, because that's how your body transports oxygen to the tissues is through your blood. Even tap water has dissolved atmospheric gases. The solubility of gases, like I kind of mentioned, decreases with increasing temperature. This is the opposite of solids. Most solids are more soluble at high temperatures. Gases are less soluble. And we can think about our experiences with soda to help us remember this. So here we've got cold soda, and you pour that, and you get some foaming here, but it's still pretty fizzy, right? If you take warm soda, especially like if it was sitting in your car and it's actually really warm to the touch, and you pour that, you get a lot more foaming, don't you? That's the gas, the carbon dioxide, coming out of the solution because it's less soluble at that warmer temperature. And this is something you could try at home. I mentioned this already too. Take some tap water, fresh out of the tap, and heat it on the stove and watch it. Before it gets to the boiling point, you'll start to see small bubbles of dissolved air coming out of the solution. That's because as you increase the temperature of the water, the solubility of those dissolved gases is less. And it comes out of solution as little tiny bubbles. When it gets to the boiling point, you're going to see vigorous bubbling, big bubbles. That's what they say, a rolling boil. Sometimes in lab, you know, we're boiling a beaker of water, and students say, "Is it boiling? I see little bubbles." Like, no, you're not there yet. That's just the dissolved air coming out. The solubility of gases also depends on pressure. And this is called Henry's law. The higher the pressure of a gas above a liquid, the more soluble the gas is in the liquid. So here we have two illustrations. Here with a dissolved gas with a low pressure and a dissolved gas with a high pressure. We can see this is high pressure because there's a lot more particles here. Basically, these particles are being forced into the water. When there's a higher pressure of this gas above the water, there will be a higher concentration of the gas dissolved in the water. Lower pressure, fewer gas molecules above, fewer gas molecules in the water. And this is demonstrated in a can of soda or any carbonated beverage. So when you open the can of soda, you hear this pop sound, right? A distinctive sound. What is that sound coming from? There's pressure. In this can, there's always a little headspace, a little empty space, where there's carbon dioxide under pressure. Because when we have a high pressure of carbon dioxide, it increases the concentration of carbon dioxide dissolved in the solution. There's carbon dioxide dissolved in tap water, but does tap water taste fizzy? No, because that is at the solubility limit. We want this solution to be supersaturated so that when we taste it, we get that fizzy sensation, right? So this is pressurized to hold the carbon dioxide dissolved in the liquid. When you open that, the carbon dioxide starts coming out of solution as bubbles. And you can see this when you open a 2-liter bottle of soda. You know, it looks like a, maybe orange soda, it's just all orange. You open the lid and all of a sudden you see bubbles start coming up. What's up with that? Well, you reduce the pressure, you reduce the solubility of the gas in the liquid, and now the gas starts to come out. And it will keep coming out until it goes flat, right?